Hey, uh, thank you. Thanks, Swadeep, and thank you everybody uh, right, for joining today. So I'm going to talk about two papers. One which was just recently submitted to ICLR, and the other that was presented at the last ICLR at a workshop at the last ICLR and at L4DC. And right, so I'll start with the first more recent work, and it's called Memory Consistent Neural Networks. And the paper focuses on imitation learning. And there's a website here where we got some nice videos. So please feel free to check it out later. But I'll show you some of the videos today. Right. Okay. So the problem that, hey, no problem. The problem that we're kind of addressing in the MCNN paper, Memory Consistent Neural Networks, is that of compounding errors. They've been an issue ever since, more traditional control theory all the way to imitation learning, even in LLMs today. But in particular, in imitation learning, when you're learning on a bunch of offline data and you are deployed in an environment online, it's very likely that you kind of take a path that slightly deviates, take an action that makes you slightly deviate away from your training distribution or your data that you have in your training data set. And eventually this leads to another issue down the line and another issue down the line, and you're really far away and you're making really bad decisions. And this is the well-known compounding error problem. And a lot of methods to address this in imitation learning traditionally seem to include corrective data or querying an expert or some form of online interaction where you can get back on the right track. But in a lot of situations, you don't have online interaction. Offline learning is very relevant today, where you only have data sets of agents doing things, and you're supposed to learn reasonably robust behaviors from this. And so our motivation was, well, what if we could design a model class that is constrained in a way that simply allows you to, not deviate or tries to avoid deviations as much as possible, just by construction. And along the way, can we also provide some guarantees? The answer is yes, and that's what I'm going to talk about today. The problem formulation is fairly straightforward. There's an unknown expert policy by star. We have some demonstrations in this situation, a bunch of tuples of states and actions. I'm sorry if I used S and A instead of X and U. I guess that's ouch. Right. I should have. Yeah, I should change it for the presentation today. Right. Everything. Yeah, that makes sense. Are these discrete or continuous? They're continuous, and they could be discrete as well. Our theory is actually on discrete domains, and our experiments are continuous. So there is this bit of a gap there, and filling it in would be helpful. But it's something that you don't have with vanilla neural networks, right? So the objective is to reduce the suboptimality gap, the gap between the performance of your policy and the policy that you're learning and the expert. And the performance gap is just a expected sum of rewards over a horizon. And our key idea is fairly straightforward and encapsulated in this one slide. We build a new model class that combines two components: a nearest neighbor function that basically for every point maps to a nearest neighbor, but also has like this exponential term that kind of weights it down away from the nearest neighbor points, and a neural network with a similar exponential weighting that basically around these nearest neighbor points forces it to become zero, and away from it expands to take as much as you'd allow. And when you combine these two together, we get something that looks like this, like a ninja star, like a shuriken. I don't know. It looks kind of crazy, but what the memory consistent neural network kind of allows is this ability to interpolate between nearest neighbor on one end, which is only going to do what's in the training data, and the vanilla neural network on the other end. And these points that I've marked in the crosses with their corresponding circles. We call them memories. It's kind of because of the fact that one, memories is a really cool word to use, and also two, they're from your training data, things that you carry over to test time to perform inference. And you'd like to stay close to these memories, but away from the memories, in regions over here, away from the memories, you'd like to do as much as you'd like to have the option to take any particular action that you like. And I guess if you've noticed over here, the neural network is kind of bounded between -1 and 1. I'll get to that in a second, but it can be scaled to any proportion with this term, with this L term over here. So yes. So the key idea is this: if you take a nearest neighbor function and a neural network and clever exponential weighting terms, you can basically simply interpolate between one of them and the other one at different regions of the state space. And that in turn allows you to get performance that simply beats like almost every baseline out there. And I'll talk about all of the methods that we compare to and build on top of, including diffusion policies, behavior transformers, and even, like, I'm not sure if you've heard of those action chunking transformers and simple MLPs. And in this plot, what you see is the percentage increase in performance in return that you get with our method over like D4RL, which is a benchmark for offline RL and imitation learning, the behavior cloning method that they provide. And the performance is significantly improved over, like, in median over about 150% for like really small demonstration data sets where this generalization is really stressed. When you have very little data and you want to deploy in an environment with just that, with just like 10 trajectories, and you have no other data, your ability to generalize to new situations in test data is really stressed. And there you see like there's a really good performance, but you also see a reasonably good improvement of 50% and above in some cases, of even up to 200% for a large number of demonstrations. Again, these are demonstration trajectories. So each trajectory can have like 1,000 transitions. So it's like 1,000,000 data points, for example.
Sorry, could I just ask? Right. Actually, this previous slide.
Sure.
Like, how are these memories formed, and how are they different from like just the training data?
Right, they are a subset of the training data.
Okay.
You can choose them with your favorite clustering method, but we found that something called the neural gas, which is like a kind of clustering that identifies like the topology of the space and tries to fit things nicely, does pretty well. But you can also just use like a k-means clustering, and that can work pretty well.
What is the feature of these memories that we want?
Right. So there are two things that we identify. One, we'd like the memories to be well spread out in the space. And I'll get to that because we want to minimize something called the distance, like the distance to the furthest distance a point is from a memory. Like, we want to make sure all points are like close to at least one memory. And so if you kind of have them well spread out in your state space, that's actually pretty helpful. But yeah, I'll get to that in a second.
I have a question.
Right.
Kaustubh,
Kaustubh,
are you able to hear me?
Just to describe the function class again, there's this. Oh wait, where's the? Yeah, I got the 1 second. Right. So there are neural network parameters over here. A code book of memories. These are the memories that you choose, a subset of your training data set, that maps a input state, now X. I'm sorry about the dissonance between X and S, but I believe that was from a slightly older version of my slides. That maps a state to the nearest neighbor multiplied by this term that allows you to interpolate in space, this distance between your current state and the memory S prime, weighted by a knob that you're allowed to play with, an amplitude knob, and again, the same term, 1 minus that, times a tanh-like activation. So the output is always between -1 and 1, times the neural network itself. So it's simply an interpolation in the output of the nearest neighbor and the neural network, and it comes with pretty good performance. Yeah.
So,
okay.
If I'm reading this right, it says that if I'm getting a state that was in my training data,
Right.
broadly speaking.
Right.
And I'm just gonna replicate the action that I saw from my
Sure.
training data.
Right.
And if I'm far away from my training data,
Not
I'm gonna
right.
or I'm gonna use the learned policy.
Right. Learned and a little bit of the nearest neighbor component as well. So that's defined
so
by
it's like a mixing of nearest neighbors.
Sure, but I mean,
Yeah.
okay, but if DX is, if DXS is like 10 and lambda is 10, then the first term is basically 0 and the second term is basically
Right.
null, right? The thing that's confusing me here is that wouldn't I expect my learned policy to do well near the training data and poorly away from it? And this seems to be trying to get my learned policy to do something when it's had no data.
Right, not exactly. So the nearest neighbor component does play a role when I'm further away because we don't choose lambda values that are really high, for example. So this is part of the knob is very important, basically. So we have seen with lambda values of like 1 to even up to 10, because the distances are particularly small, that the nearest neighbor plays a pretty significant role in actually making sure that you're not doing something completely stupid that the vanilla neural network tries to tell you to do, but you're just doing something that is a little more reasonable plus a little bit of stupidity that's acceptable.
I mean, I guess
Right.
that makes sense. But then
Right.
in that case, why do I even have to train F data? Like, what if I
Right.
what if I just put in a random neural network? Wouldn't it still be okay because I'm still constrained by the nearest neighbor?
Right. So if you have a lot of memories, you can throw in a random neural network.
Sure.
But if you have a lot of memories, your inference is going to be really slow. And it's unlikely to have a lot of memories when you have very few demonstration trajectories in the first place. So under the constraints of small data, the neural network actually does help generalize to some extent beyond what you've seen in your training distribution. And not to the extent that, not to like really far away, but to a certain extent that the nearest neighbor obviously cannot do.
Sure. I mean, certainly, right? Like, but I need to think about this more. But
Okay.
The thing that I'm struggling to reconcile, I'm sure
Right.
I'm sure you'll address it, is that at least our experience with notation learning is I trust my policy on the training distribution.
Right.
And here you're basically saying I only even use my policy when I start to wander away from the training distribution.
Right.
And
Right.
that's what's confusing. Like, do you
Right.
understand where the confusion is coming from? I'm
Yes.
not saying that
Yeah.
this doesn't work.
No, right.
I don't understand why it works.
Right. That makes sense. So, okay. So the reason, okay, that's a good point. But I think there's a different way to look at it, which is I trust my policy a little distance away from my training distribution, but not too far away. And if I'm very close to my training distribution, I might as well use my training data. But if I'm a little further away, I can't use my training data, but I trust my policy to that extent. But I don't ever want to be that far away from it that I'll never trust both.
I see. Okay, so
Yeah.
so you're not envisioning ever using this where all of the weight is on the learned policy.
Yes, no.
Okay.
So you're saying something like replicate if exactly, and then smoothen out a little bit by the way.
Yes.
Can I think about it like that?
Yes, sure. And the point of this is that you never get to a point, like ideally, because of the constraints, you'd never go that far away that you can't trust either your training data or your neural network. But in practice, yes, you do end up messing up sometimes, but overall, much better performance.
And when you train your policy F data, it's just part of this composite.
The whole thing, the
Okay.
whole thing, just back propagate through it. Yep. I'll get to that in, yeah.
So I've never worked on this problem and also on imitation learning.
Okay.
But the plot that you showed before looked a bit like Bayesian optimization.
Right.
It's like a
Yeah.
GP,
Yeah. I don't know much about I guess the Bayesian way of looking at things, but yeah, I see the similarity to this in like the Gaussian process,
And
plots
then you
and
have
things
data
like that.
and then the variance.
Yeah.
Right.
Sorry.
Right. That's this part is not really, this part is just a depiction of what happens because of this E term that kind of reduces it. So it's not really uncertainty that I'm depicting over here. It's just the possible space of outputs that my neural network can give me. So while the plot looks like the Gaussian process thing, it's not exactly the, yeah. Right. This is not uncertainty. This is just the space of outputs from the neural network. Yep. Yeah, I've seen that. Yeah, that makes sense. Yeah. Okay. Right. So how do we cluster? So in the start, we were looking for an algorithm that can basically give me something to do inference really quickly. So if I'm at some point in the state space and I want to find a memory for my next state, I shouldn't have to search through everything again. Graph search proved a helpful a way to kind of limit the amount of searching I'd have to do. And so we went for this algorithm that provides this really nice graph of points called the neural gas technique, but which took it off the shelf. But you could also just use another clustering method. But we have seen that for some reason that we don't understand yet, neural gas provides memories that give me better performance downstream, but we just don't understand that yet. But also, the whole reason of going for a graph for faster inference was proved unnecessary, because in the end, it's just much faster to throw the search problem onto your GPU and like just let the GPU run. And yeah, so yeah, GPUs are great. Just do batch searching and don't think about inference. And I mean, this is not great advice, but yeah, it seems to work in practice. That's just a side note. Right. So how do we actually learn the memory consistent neural network? Fairly simple. Sample a batch from your data set, backpropagate through your loss function, which is in this case just the mean squared error for an MLP. But it could be more complicated loss functions, as you'll see down the line. That we use the MCNN on top of an MLP, on top of a behavior transformer, where there's a combination of a cross entropy and a mean squared error term, and then on top of a diffusion policy as well. So that has like multi-step mean squared error with the denoising process. So it's like, doesn't matter what loss function you use, as long as you take your backbone, throw it in here, and just backprop to the whole thing. Right. So right. So there are, I didn't put all of the theory in here because I didn't want to go through it step by step. But I think there are 4 key points, starting with our assumption, which is a bit strong to some extent, which is that we assume that the expert policy belongs to the function class we choose. So yeah, sure. If you had a really huge neural network that covers a large possible space of functions, this is not an issue. But yeah, this works well with like 2-layer MLPs as well, which don't cover every function there is. So, but yes, if you assume that, and I think this is the point that you kind of raised the question about before, which is what is a good characteristic to have for these memories? Well, we'd like, we define something called a most isolated state, where for a given set of these memories, we literally find the distance to the most isolated point, the point that's furthest away from any memory. And this point is fairly integral because it goes into our bound. And the smaller it is, the better our bound is, and also our performance in practice. And the width of the function class, basically, it's a lemma that we proved that states that because we've constructed a function class this way, it is always bounded by 2 times that constant L times that 1 minus E term. But instead of any distance, it's that distance to the most isolated state. And because we have a function class, unlike vanilla neural networks, that's actually bounded in width, you can just bound the suboptimality gap directly, because you can use this width in the TV distance and then use that directly in existing suboptimality gap theorems, and we get a bound that basically states that your suboptimality gap goes down if you have more widespread memories and in general more memories. So just to get to the more informal guarantees, well, the MCNN function class is bounded in width, even though it uses neural networks as a backbone. And this, which you can't have with vanilla neural networks, and this translates to a bounded suboptimality gap, also not available if you're just doing imitation learning, if you're just doing behavior cloning with a neural network. And more widespread memories, to a certain extent, just in general, lead to a lower performance gap. So yes, if you did use all of your training data points as memories, you only have the nearest neighbor function. You don't have the vanilla neural network. So in practice, that's not good. That's why there's the up to a limit over here. And so in practice, we noticed that this about 20% of the data set is like a good limit to have for your for the number of memories you want to use.
You're splitting your data set into memories and supervised training data?
No, so at the training data points that are the memories, you have a loss of 0 anyway. So,
Right, okay,
so it doesn't really matter.
That's right.
Yeah.
Can you repeat what you said about like using 100% of the training?
Right. So if you use 100% of the training data set as your memories, you'll never be able to train your neural network, because for every point the loss would be from the nearest neighbor, which would be like 0, because it's exactly giving you the action in the training data. Right.
So the assumption that you have for the expert policy block to the block apply.
Right.
And I also think that is some sort of smoothness assumption, because you're saying that given your memories, like your variation is sort of bounded in between those
Right.
points, right?
Right. Absolutely. The variation is bounded by that L term. That's kind of important to even bound our the biggest possible input by the smallest possible input. So bound the function class. But I think I'm not sure. I'd say smoothness is just in general that the maybe Sadeep can.
Yes,
Yeah.
and also by the realizing that you still have to be able to realize.
Yeah.
The neural network class you should be able to.
Sure, yeah.
Like I could have a small MLP, I could have a small function class that is smooth, but my expert doesn't really take a function from this function class. Right?
I mean, yeah.
But given modern DNNs, yes, that smoothness is the main.
Right. Okay, so maybe I can move this a little below. Right, or maybe up there. Okay, so we evaluate the MCNN on dexterous manipulation tasks in D4RL, which is a offline RL benchmark, where you have these 4 tasks for manipulating a pen, using a hammer and hitting a thing, and then relocating a ball and like opening the door. And also in Carla, where you have to drive from one location to the other while staying in the lane. This happens from images. Over here, we use like state spaces. And for the images, all we do is we take a really good off-the-shelf encoder. We encode the image into a 512x1 vector and just continue working with it like it's a state space. We don't actually fine-tune the encoder because to some extent, perception has got pretty good, at least on existing benchmarks. So yes, you can work with either images or proprioception. And our evaluation metric is fairly straightforward. The environment comes with a reward function that we don't use while training, but we use to evaluate how well we've done. The baselines that we compare to are a bunch, starting with a simple MLP and behavior cloning. This really popular new baseline for using diffusion models for behavior cloning, for using transformers for behavior cloning, for using implicit models, energy models, like Lyapunov functions for behavior cloning, and also like an offline RL algorithm, fairly common offline RL algorithm called CQL, but we only use a reward of 0 or 1 for task completion. And also compare to one nearest neighbors and to also something called visual imitation with nearest neighbors, which is a recent algorithm that basically performs k nearest neighbors on the embedding space of images. And I'll show you the results in there.
Where did you get your experts from? Did they come with U4RL?
Right, the D4RL provides a data set, so we don't have like a real expert. They just the data set is the
They
occupation.
give you a data set of expert demonstrators.
Yes, yes. And for the Adroit environments, the demonstrations are kind of small. They're like 10 trajectories and total of like 5,000 transitions. For the Adroit human demonstrations, where humans have actually like manually made the simulator do all of this stuff. And there's also Adroit expert demonstrations where they trained an RL policy in the Adroit environment, and after it was fully trained, they obtained demonstrations. So then those are like 1 million data points. And Color also comes with like 100,000 transitions, maybe like 100 trajectories, basically. Right. So baselines, data set, and now architecture. three standard things. So our MCNN is applied on top of an MLP with mean squared error. Like I mentioned, that's the simplest thing to do. It's also applied on top of the diffusion behavior cloning models that just does mean squared error, but multiple steps of it. And the behavior transformer, which again kind of predicts an action in a particular bucket first, and then a particular offset from that bucket. So it's just a combination of cross entropy and mean squared error. And yeah, some of our results on the adroit human tasks. So if you'll notice the bars with the dashes on them, the crosses on them, those are our methods. And the starting the one at the left is simply D4RL's original behavior cloning baseline. And then there's one nearest neighbors, there's a form of k nearest neighbors baseline that is common in imitation learning. There is this offline RL method with 0-1 rewards. And there's implicit behavior cloning, which uses these energy models to avoid compounding errors. And then there's the simple vanilla neural networks that we use as our backbones for MCNN, which is the behavior transformer, the diffusion model, and a simple MLP. And I think a few things to take away from like some of these plots. For example, you can notice that MLP plus MCNN does the best over here and over here. And MCNN plus behavior transformer does the best here. And we're sadly beaten by implicit behavior cloning on the door task. And I think the important takeaways here are that one, like on every plot over here, you'll notice that the bars with the crosses beat the bars without the crosses. So that means the MCNN plus a neural network beats the simple neural network. And also, another interesting thing to notice is that while diffusion, for example, a really recent model is better than an MLP in some of these cases, like here, and like here for sure, much better than an MLP. But adding MCNN to the vanilla MLP makes it much better than diffusion. So just adding MCNN to a really standard, really simple neural network just makes it better than something that's come out pretty new.
How sensitive are these results to the choice of your memories, and how hard is it to find the right set of memories for this plot?
Not at all. We simply use like 10% of the data set for creating our memories, and we didn't, and they just work off the shelf. So all of these tasks, I think I don't have that here, but all of these tasks, the MCNN methods use the same hyperparameters across all tasks. So in offline RL, you're not allowed to tune hyperparameters because that's kind of cheating. And so we use the exact same hyperparameters. So like all the diffusion models use the same hyperparameters, all the MLPs use the same hyperparameters, all the behavior transformers and MCNN behavior transformers use the same hyperparameters. And for all MCNN methods, we use a lambda of 1, an L of 1, because the actions are between -1 and 1. And yeah.
So if you had like, so what is the total number of data points that you are using?
Right. So for the human tasks, there are about 10 trajectories and 5,000 transitions. So each trajectory is about 500 steps. And in the expert tasks, there are about 1 million transitions. And yeah, there are about 1 million transitions and about, I think, 100 trajectories or something, basically.
So if you had like just 2 or 3 trajectories.
Right. So that's a good question. We haven't tested our 2 or 3 trajectories because the simulators themselves, they have like a bunch of, like every time you reset the simulator, it starts from a different initial position, a different setup of the ball in the relocate task, a different way you're holding the pen. Maybe if I show you some of these, like for example, in the pen task, you can see that each different reset of the environment, you have to move to a different pen position. So I don't think in these tasks particularly, it'll be easy to do this with 1 or 2 simulations, because it's not like 1 or 2 demonstrations, because it's not like you have one fixed goal in one initial condition. But yeah, if you could, that would be really cool too. And I think Farhad was working on something about one demonstration and like yeah, but I assume he needed like a dynamics model as well. So that's something. Not really. Is that
You
okay?
learn the model from the demonstration.
Yeah.
Okay. But it's learned from the demonstration. So
I think Farhad is asking if he can hear you as well.
Oh shit. Okay. Hello.
Hey, can you hear me?
Can you hear me? Or is it?
Yes, I'm able to hear you.
Oh shit, I think my volume was low. I'm sorry about that.
No problem, no problem. So I want to ask a question here. So at inference, you are basically choosing some point from the memory, right?
Right. So I get a state
Given you.
of the memory and then I forward prop through my MCNN.
So how have you observed the computation time for that? How fast
Yes.
is it? Like,
Everything happens on GPU, so it's almost instantaneous.
oh, okay. And you're using 10% for your memory, right?
10% of the data set, and it works even with 1,000,000 data points. So I just have to do an L2 distance between, you know, 10% of 1,000,000 and like my one state, and that happens instantaneously.
Okay.
Thanks to NVIDIA. Yeah. But so yes, in these particular cases, I'm not very sure how it would work with one or two demonstrations, but that's a very interesting.
But I
thing to
guess,
check out.
to like talking about Farhad's work, if you had like a learned dynamics model for every initial condition for which, then you should be able to do this with
Right,
you
but
learn a policy that's
right. I that would be great. But again, I'm not very okay. So I don't really know a lot about Farhad's work. I should look into that. But I'm not sure how you'd be able to learn a dynamics model with just one trajectory if the dynamics are fairly complicated, like a dexterous manipulator.
So
Is
I think there's the disconnect here is the application that we're looking at.
Right.
It's human robot interaction where
Okay.
we're getting like one or two trajectories of like kinesthetic teaching of a robot.
Okay.
And we want to make sure that we basically want to learn a vector field that replicates that demonstration on the training data.
I see.
And then we do something to shape the vector field away from the training data so that it comes back to the demonstration.
Okay.
So in that case, the basic idea is we basically overfit a neural ODE to the data.
Okay.
And then we use CLF, like control the app and off
Okay.
function type methods to kick ourselves back to
I see.
the training data if we have moved away. And we're motivated by different things. They're never trying to be like reactive to, during the execution, a human comes in and moves me away to where I haven't seen any demonstrations.
Right.
I mean, I don't have any data, so I can do what I want with it. And what we're saying is the reasonable thing to do is go back to where I have data.
Right.
So, but it's very different from what you're thinking about.
Right. No,
I
that
mean, it
sounds really cool.
you know,
Yeah,
Because
yeah.
the whole intuition behind
Compounding.
reading those shaded regions was that when you're away from your memory, you should not go too far away in terms of what actions you take. So
That's
there's
fair.
still that bounding nature to it, and that's what shows up in everything. But yeah, that's basically a lot of offline. The intuition is the same.
Yeah.
Yeah, that would be very
No,
interesting.
that's cool. That
Try
sounds awesome. Yeah.
Yeah, I mean, I think like philosophically, I think they're aligned, right?
Right,
The question
right.
would be,
The application. Yeah.
if you think of I don't know, I'm gonna make something up here, but like a mixed autonomy setting where the robot deviates from what the human showed them in a way that's interesting or something.
Right.
No, why I asked like again how fast it is. This was something which we have been thinking about also, like what to do when we move away from our training data, right? But what you're doing is really counterintuitive because you're trusting the neural network when you're away from your training data.
Right. To a certain extent. And we make sure it never goes that far that we can't trust it anymore.
I feel like that's kind of solved by the fact that you have so many demonstrations. Right? Is that not true?
I don't think so. For example, if you just did vanilla behavior cloning, that's where you just trust the neural network only. And those are your light blue pods, for example, over here, and over here. There's like a significant difference.
So
Yeah.
I think I understand what's happening here because of the architecture that you have and the way, and you're training the neural network as part of this architecture.
Right.
What you're really training in this F data is an interpolator between.
Yes. So that gets exactly.
It's kind of like
Yeah.
two memories and then in between it,
What is the-
interpolating with the neural network. That's really what you're learning.
Exactly. And that also kind of motivates what we're working on right now, which is learning the interpolator for a bunch of tasks. That's exactly right. Yeah. We're learning an interpolator between memories. So you don't have to remember the action for every memory. You just have to remember how to interpolate.
So if you do get kicked really far out of your training distribution, this probably won't help. The idea
Right.
here is that I can get kicked out a little bit, and because I've learned an interpolator, hopefully it'll interpolate a little bit and bring me back.
Exactly. And yeah, and to some extent, we benefit by the fact that in high dimensions, this interpolation is to some extent like extrapolation. So, but I mean, there's a debate about that, but yeah.
Yeah, Lincoln's word is a gospel.
Yeah.
So let's-
I completely agree, but I'm not sure that this isn't right because that seems to be why a lot of neural networks have
The
a
opinions
lot
of the speaker, it's not a reflection of the other.
not a reflection of the other authors for sure. Yes.
So I
Yeah.
think, I guess what I'm a little confused about is that my understanding of like, in general, I thought neural networks should do some kind of interpolation, but isn't that how like generalization process? Empirical discrimination, all that assumes that there's some kind of.
Yes, but like, we never explicitly constrain. Like, this is really making it explicit that that's what you wanted to do. I think there's something implicit about interpolation happening.
Okay.
In the ERM, this is saying this is exactly what we wanted to do. At least that's what the architecture says. I don't want to put words
Right.
in your mouth.
I agree. I agree completely. And yeah, explicit interpolation is great. So,
And another question here, is that the term which takes care of interpolation is it fnn of x or the f theta of x in your neural network architecture?
That's the neural network. The FNN, yeah, I'm sorry about the terminology. NN there was nearest neighbors.
Okay. Right.
Theta was the parameterized neural network. Yeah.
Right. Okay.
I think I need better.
That's okay. Have you observed how far, if you are away from your training data, that you are able to get good enough performance?
Right. So I can't generalize from one Carla map to another, but within the same map as this plot shows, I'm able to do pretty well.
I like have you stress tested and like given it a state that's very far away from what it's, you tested how far you can go while it still gives you something reasonable.
Right. So I did have an earlier plot of like distance versus like the loss from the memories, but that didn't make it to the paper, but I can look it up and get back to you. But no, we haven't completely stress tested this. That's a good point.
Yeah, I think it's interesting, whatever comes out of it.
Absolutely.
Yeah, I have a question. So I find the fact that you don't need to give too much hyperparameter to be very concept driven. Especially,
I think there's a little bit of a cheat code there in the sense that so we did have to tune hyperparameters on one environment, and we spent a lot of time on that. And I just used the same hyperparameters on the other environments and got good results. So I didn't spend a lot of time on the others.
nice. So what I was thinking is that like finding this L really constrains like how much relation you're
right.
Like that.
Right. So a good choice for L seems to be the absolute maximum of the output of your neural network. So in your data set, if you're mapping states to actions, like all of our actions in D4RL are from -1 to 1. So we just take L to be 1. Yeah. Good points though. I think the whole hyperparameter selection thing is very weird in offline RL and is not that great. But
have you looked at trying to also learn the metric that assigns a distance between the state and the memory?
Good point. No, right now we're just using an L2 distance, but yeah, we could learn an operator, we could learn a metric there, we could learn something.
So that only becomes useful if you have like
embeddings
like
of image, which is what we have in Carla, but even L2 distance works.
What applications do you have in mind? Interesting metrics.
Like by simulation.
There's no reason to think that L2 is the natural metric.
I agree.
Thinking about these things, right? If I have something that lives on a sphere, something else might happen.
Right.
Sign similarity might be the right
Right.
But I agree that this only becomes interesting if I have a lower dimensional manifold living in some higher dimensional ambient space.
Right. Yes.
Yeah,
That's something to look into.
I'm curious.
Right. I already showed you this. Moving on to okay. Also, if you vary the number of memories, we find a sweet spot generally around like 20% of the data set. And also, if you simply train a bunch of these with different hyperparameters, and you just have like 20 episodes online to test which hyperparameters are good, you can get even better performance. It's kind of like fine-tuning, but I'm not fine-tuning the parameters. I'm just doing selection of the hyperparameters online. Okay. And shortcomings, more hyperparameters than vanilla neural networks. heavier at inference than a vanilla neural network because you still have to search, but it's lighter than like one nearest neighbors and the other method because you don't have to search amongst the whole data set. You only have to search a subset, the memories. Yeah, so right now we're going beyond nearest neighbors to learning to retrieve. Basically, the work I'm working on right now basically takes the multi-game decision transformer for Atari and tries to play new games ideally within context learning. And the goal is that we go from nearest neighbors to learn retrieval and from a task-specific policy to a more general policy. But an extension that we could be looking into in more detail, we just briefly looked into it, is offline RL, because again, robustness to compounding error is philosophically and fairly in practice similar to conservativeness in offline RL. And could we get like more interesting guarantees in offline RL on like performance given certain constructed models or other learned models? So that's I guess maybe something to look into. And I can quickly go to the other paper. Do I have? Okay, it's 460. Maybe I'll go through this a little quicker. The other work basically has a similar structure to the first paper. This is slightly older work at L4DCN and ICLR workshop. That was called Guaranteed Conformance of Neurosymbolic Models to Natural Constraints. And here, what we've kind of been working on is basically building dynamics models that respect physics and medical constraints. And yes, ideally, you use this for a bunch of our motivation was fairly straightforward. Neural network models don't respect. They're used everywhere, but they don't actually respect physics and medical constraints. But you have a bunch of these models or simulators available, and traditionally they're kind of black box in nature. I just threw Mujoko on there, but realistically, you also have these artificial pancreas simulators that are just a bunch of random MATLAB code and other components, and that have been used like historically for a long period of time, but they're like fairly black box in nature. They also have like random equations that nobody can understand. And I guess the point is, that if you have a bunch of these black box models, specifically, not just differential equations you can write out by hand, how do you conform to constraints provided by these models? And this is an example here is, if you trained a policy in Carla, not on images like in the previous paper, but just on states of X, the expression Y position, your heading, as well as your velocity and your rate of change of your heading. And you just try to predict, for example, the next state or just the next X position, Y position and heading. A simple thing that this model should adhere to, provided as many demonstrations as you want, is that when given zero steering and throttle, these two terms, it should not move. It should give you the same state as before. But in practice, we've seen that if you train a simple vanilla neural network or throw the constraints, in this case, we just wrap them up as the unicycle model that represents the Newton's laws. If you throw them into the loss function and you learn a weight for this term through the augmented Lagrangian loss, it still doesn't do well in practice. It predicts that at the origin, given zero control, that the position changes like this. And yeah, so a lot of this is they actually really work poorly in practice. And our contribution was that, well, we have a better way to, by construction with memories, as you saw before, constrain them to make sure that they don't make as big of an error as augmented Lagrangian, and in practice, but in theory, guarantee that they should not make any error at all. Basically, up to some delta distance. In theory, guarantee that they'll make an error up to some delta distance, and practically observe that as well. And yeah, so that was the motivation for this paper, where we're trying to build these dynamics models that only make a small error and they stick close to the constraints given by some model, physics constraints, medical constraints, etc. The problem formulation is again straightforward. We're trying to learn a model that maps X state and U control to the next state XT plus 1. I'm sorry.
X and U are S.
Yeah. Yes. So yes, I'm sorry about that, but this is also a bit of bad terminology. So we combine X and U to call it S because we want to map inputs to outputs. But given this data set of inputs and outputs and a black box model that we want to stay close to and a parameter of how much we want to stay close to it, we're trying to simply minimize the
Wouldn't your data set be like S0, X1, S1, X2?
yes, of course.
If
Sorry.
you're looking at it, you're right, if you're looking at the trajectories, but this is, we are looking at it as training data. Like input,
Yeah.
But if you're
S is X0 and yeah.
The loss function doesn't make sense because you're regressing
Right.
f of X0, U0 to X0.
So
That's not what you want.
yeah, so I guess I think there's a bit of an issue here. No, there is an issue here. That should be an XT minus 1.
Okay,
Yeah.
okay. I just want to
And
make sure that
XT.
that's what you're doing.
Yes,
Okay.
of course. We're just learning a dynamics model that predicts the next day. Yes. I think we got carried away with the notation over here because we just wanted to make it like it was
That's hard to read.
yeah.
Success.
Right. Yes. So we're trying to minimize a mean square error while trying to stay as close to the constraints given by M. And the key, sure.
How was delta chosen, I guess?
Given by the user of this tool / algorithm.
Oh wait, sorry, can you go back to the last slide? How do you enforce like that delta?
Right, that's exactly what I'll tell you the next thing. Yeah. Oh, okay. So the key idea is similar to before. We have a bunch of state action tuples we have a bunch of X and state action tuples, and we're trying to simply cluster them to learn memories. Again, we use the growing neural gas here, but you can use any clustering method. And we build a partition of this space where we use the memories as centers of Voronoi cells. And for each Voronoi cell, we build a lower and upper bound that the outputs of all the points in that word, like all the possible things that all the points in the Voronoi cell can map to. So that's exactly how we enforce that. For any point in this Voronoi cell, it should only be here. No, this is how we find out what to enforce. And the way we actually enforce it is with another construction that allows me to enforce it by construction. With another model that allows me to enforce it by construction, enforce constraints by construction. Basically, a neural network constraint, which we denote with the gamma, with this operator over here, takes in an input point S, maps it to the lower bound, this thing up here, and adds a sigmoid of an output of a neural network times the upper bound minus the lower bound for that point Voronoi cell. So that way we're making sure that every state, every input always maps to an output that is within constraints that we've calculated beforehand.
Am I wrong in thinking that if you're in a very high dimensional space, computing these, like representing these Voronoi cells and computing the corresponding upper and lower bounds would be expensive?
So that's true, but in the sense that we don't actually have this issue in practice because we sample points, propagate them through the model, and then propagate them through the constraints, the M, to find this lower and upper bound. And we have basically a guarantee that says if you sample enough, then you can, this shouldn't be an issue at all. And in practice, we don't see this as an issue because we work with up to 120 states in an artificial pancreas model. So that hasn't really been an issue.
But sample enough depends on the dimension, right? That enough.
That's true. Depends on the dimension. So yeah, so that's true. That's a limitation to some extent. Yes,
So,
but
okay, so the key part here is because of the neural gas. So one of the advantages of the neural gas, and while he has been doing the GPU selling angle, the reason of the neural gas is one is it's easy to look up, and the other one is it gives you a natural partitioning along the graph of where the data lives in itself. So even though the dimensions can be high, usually if you have like 1 million points, you have a very good understanding of where in what subset the data lives. And if you have an understanding of that using the graph on the left, you have a concrete understanding of where these polyhedrons are. And once you know where these polyhedrons are, computing those interval abstractions are very easy.
Might be a dumb question, but like, why should you learn car dynamics models?
Right. So if you're working, for example, with model-based RL and you want to, for example, figure out what you would like to, what the consequences of your actions are in the future, this would be helpful. Given you're learning a model, sure, there are issues with, for example,
I mean, in the plot that you showed, you are using like an X, Y, theta, like the unisex.
right, this is just
Example.
an example. Ideally, you would learn a much more complicated card.
Yeah, so once you start learning from images and stuff, won't the dimensionality become a problem?
So again, it hasn't been a problem because, for example, right, okay, that's a good point, because in the first paper, when we projected the images to a vector space, it was 512 dimensions, and the maximum we go up to here is about 125. But even there, the thing that takes the most amount of time is in creating the neural gas. And if you just clustered with something else, maybe k-means, that would be really fast. And learning this neural network is not really an issue, because it's fairly easy to sample points and then propagate them through a constraint model. I'm not sure what this constraint model would look like for inputs that are image embeddings. So, but if you can propagate it through the constraint model easily, the dimensionality is not an issue in practice. Right. So there's basically model data set loss, back to the basics. The model I already talked to you about, the data set, basically, we have some label data. We also have the ability to sample data points from regions of interest, such as if you can just randomly create X, Y, theta, throttle 0 and like throttle 0 and steering 0 points. So this way you can sample points from regions of interest. And all we do is we minimize the augmented Lagrangian over basically the labeled data points and the unlabeled data points, which the augmented Lagrangian just consists of your mean squared error term, for example, over here, and your constraint satisfaction term. Your constraint is just delta minus this, should be positive. And yeah, the augmented Lagrangian comes with few other perks, like squaring up the constraint and only choosing this if the lambdas are positive and etc. But basically, you throw the constraints in the loss function along with your chosen loss to learn the model, such as mean squared error. And how do we actually evaluate this? Two criteria: the approximation loss, how well does my model actually fit to the data, and a constraint loss, how well does the model conform to constraints. And our guarantees are also, I guess I'm running very late, but our guarantees are also fairly straightforward. We guarantee that the model will respect the constraint up to the desired delta. And the only negative part is that your approximation error becomes slightly higher than a vanilla neural network. And that approximation error becomes slightly higher by a term that is proportional to the size of the largest Voronoi cell. So again, if you had more memories and you had more widespread memories, you'd have a smaller increase in approximation error. These are some plots with just showing you that there's a slightly higher approximation error, but much lower constraint loss. And these are the nicer looking GIFs, basically, that I showed you before. And we have similar situations for the artificial pancreas model, where the approximation error usually increases, but can be approximately the same as well. But the constraint loss is significantly lower. And the constraint that we'd like to satisfy here is that if you increase insulin, the glucose amount should decrease, basically. And we see that kind of qualitatively as well. We see the number of violations of this constraint to be much lower in average and at a maximum for our constraint models with different numbers of memories. And for drones, where we try to make sure that at hover, if they are provided zero control, they shouldn't move. And yeah, similar shortcomings exist. Additional hyperparameters, slightly more overhead, and an additional shortcoming that we completely got rid of when we worked with memory consistent and not memory constrained neural networks in the first paper that I talked to you about, which is prior information in the form of your constraints in the form of the black box model M. And here, at least we do believe that some future work could be in the fact that to lie somewhere on the spectrum between no prior knowledge to lots of prior knowledge, but also obtain obviously lower approximation and constraint loss. And when the neural networks are like down there, and you have physics informed neural networks where they're only usually applicable with the white box model M, and you have constraint layers where you have to carry this constraints with you when you're doing inference that you don't have to do in our situation. And you also have the augmented Lagrangian whose loss function that we use as well, but just get better performance because of the construction of our neural network. So yeah, if you're interested in physics and medicine conformance, please consider using our code and let me know if you have any issues.
Calling it a neurosymbolic network?
Right. So that was a bit of I guess we were two things. It has two components. Similarly, so we consider our memories to be a form of symbolic component, and the neural network to just be the neural part of it. And this was taking a bit of a liberty with the term. So traditionally, you'd have more all the work from, I forgot the name of that person at MIT. But yeah, so this is not like the other neurosymbolic approaches. We did take a little bit of liberty with the term, and we mostly called it that because of the memories kind of being like symbols that are fixed that you have to carry around, and the neural network just being the neural component.
Since you called it neurosymbolic,
right,
I'm going to ask you questions related to that.
Sure.
If I gave you an LTL specification,
okay,
could you convert that into? Can you bake that
Yeah.
into your network?
Yes, of course.
I mean,
How would that look? Because I mean, I can see the output of the model. I guess what is a black? How does the LTL automaton that comes out of that map onto this picture?
Right. So yeah, I can probably attempt to answer that. So the reason is so let's say why would you give an LTL? Probably you want the control policy to and so trivially, by LTL you probably mean in realistic spaces with the STL, like signal and flow.
Not necessarily. It could just be like do this before that.
Oh, do fine. And if you know what this and that are, you can probably create convert them into the quantitative semantics of the formula. And then that would become the symbolic model, which is the symbolic knowledge. And then that symbolic knowledge, and the reason we call it symbolic was because this we were creating a numerical wrapper, which is based. So this is basically a numerical wrapper for the model,
neural network,
and which is enforced through these symbolic constraints on the neural network. And so you could convert the LTL into this
quantitative semantics, get a delta on how far you want it to be, propagate that, get your green layers, and then just train the neural network, your policy.
So can this, like if you want to speed up like constraint optimization?
Oh, I see, like MILPs?
Yeah.
I'm not sure how they work internally. I'm happy to just use the solver off the shelf.
Like branch bound is very slow.
Okay, branch bound, sure. That's I need to think about that a little more. I'm not so yeah, I'm not sure how. I guess if you can map it into like the policy situation, then it shouldn't be that hard. Should I branch here, or should I just stop? It would be similar to the LTL situation, but yeah, I'll have to get back to you on that. I'm not going to give you a good answer right now. Okay, yeah, so that basically concludes the MCNN and the conformance of models. And any more questions?
I have a question.
Sure.
So how are you exactly getting the sampled data set, like the unlabeled data set?
Right. Right. So, for example, because we know what the inputs, let me go to the car model. So here it's just, we have a data set of inputs, that's X, Y, theta, the throttle and the steering. And we know the maximum minimum of that. So we just randomly uniformly sample X, Y, theta there. And the throttle and and steering we set to 0, because we're interested in these special regions where they have to respect constraints. We're just sampling more points in that region. We also provide all of these points to like the vanilla neural network to make sure it's a fair comparison, but to the vanilla augmented Lagrangian to make sure it's a fair comparison. So it's not like we have the extra points. It's the same points for everybody. But the way we sample it is just sample x, y, theta within the lower and upper bounds of what's in the data set and set the other two to 0 because that's what we're interested in.
Okay, so that depends on what type of constraints you're
right. The regions of interest that you care about.
Right.
Such as a car at rest, the drone at hover, artificial pancreas that ensures that glucose goes down when your insulin amount increases.
Okay. Okay.
That's a naive question.
Sure.
So there's two things that I've seen people do in this situation. One of them is like just data augmentation, because I don't know, it hurts my feelings a little bit that zero input does not lead to like a notion of zero output. That is just, I don't know, that deeply like offends me. I don't know, because it's like that works in a linear model, like, the fact that it doesn't work in a neural model, that
2-layer MLP. That's
that's very surprising. So and I didn't see you mention like just the
so we provide these augmented samples to like the augmented Lagrangian as well. That's the loss function without our nice wrapper around the neural network. That's the orange line.
Wait, is your augmented Lagrangian an augmented Lagrangian in the ADMM sense, or augmented Lagrangian and you augment the data and then
no, it's an augmented Lagrangian in the loss function. So we take the constraints to the loss.
Yeah,
and
exactly. Okay. And so what I'm saying is that data set augmentation.
Right. So the data. So okay, it's both. Sorry, it's both in the sense that we have these unlabeled samples that we also provide to the augmented Lagrangian. So we both provide additional data, and we also have the. So it's augmented data, augmented loss.
Yes. Okay. So there are two augmentations out there.
Right.
Okay. All right. And it still doesn't work. Zero input.
It doesn't work usually if you stress test all the hyperparameters. I have not got it to work for this condition and for a few other conditions, but it does much better than the vanilla neural network. And you can kind of see that on like this plot, for example, where the constraints are like reduced. This is a log plot on the y-axis. So it satisfies constraints almost an order of magnitude better than the vanilla neural network.
I mean, yeah, sure. I guess it's just like.
I mean, also, why would you think adding
it's just the loss function
or adding another bunch of data would fix it when even for images it was right? I mean, that was the argument that was in the training, that you add some adversarial examples and it might start working with adversarial examples themselves. You can still attack this.
I mean, my intuition is just like literally the people who work next to me in Alejandro's lab, they just like when they explained to me that the training pipeline they use for CNNs and whatever, how they train for the constraints is exactly that. They just augment their data. I mean, okay, some people, it's not everybody, but how they do it is they augment the data set and they have the augmented Lagrangian, same thing that you guys do. And this augmentation that they do, then what they do is they learn what the cost would be, those lambdas,
in the augmented Lagrangian.
Learn how to update those lambdas to better sample, to better generate. Okay, I'm not going to use the word augmented data set anymore. I'm just going to say fake data, right? So they
we don't do the fake data part.
It's like it's like they say, here's an image that we know should be classified as such. We rotate it a little bit, or we translate it a little bit, or we flip it, depending on what our classification is.
Sure.
So this is what they do. And then they say, you should all classify to be the same, right? And this is just for an image classification. It's not the same as what you guys are doing.
Right.
Right.
So
say,
I guess a point here is that, well, even for adversarial training, right? Like if you simply augment the data in the start, it doesn't work. Adversarial training only works when each loop of updates, you generate new adversarial samples with the current iteration of the neural network, and then you add that and then you train on that. So I guess maybe if yeah, maybe it works better for flips and this thing compared to like adversarial examples. But I guess yeah, that's a.
I guess I've seen it work like surprisingly well, and it made sense to me. And it's like you're just changing your. I mean, I shouldn't say you're changing your cost. You're changing your training data set, kind of, right? To better
Maybe right. That's a good question. Maybe it's a feature of scale. We're dealing with small data sets here.
Yeah.
So maybe as you scale up, it's all good.
I guess it's just, so
Yeah.
that's another thing which is like very different. We are looking for guarantees here.
No, that's fine. Guarantees are good, right? I'm just.
But if they
Zero
work,
input does not lead to zero output. That is extremely sketchy. Like that is scary.
Yeah.
You know that happens.
I mean, given what neural networks can do, I don't think it's sketchy.
Yeah, so that's what there's a couple things. Like, it's really easy to just by construction have a neural network that if the entire input is zero.
Yeah.
It'll be
the
zero.
output is zero. You just
Yeah.
get rid of all the biases, right?
Sure, yeah.
That's fine. But neural networks like MLPs are not good at multiplication. Right? So if you want there to be if you want to kind of guarantee that zero inputs give you zero outputs, like for the UPenn model, right? Really what it is, it's a control affine. So you're trying to get your MLP to learn G of X times U.
Yeah.
MLPs suck at multiplication. So it's not necessarily surprising that so if you use like an attention mechanism, maybe you would learn faster, right? Because the attention mechanism can do the multiplication.
Right.
But MLPs just like I think you need something like if you want epsilon approximation multiplication, you need log 1 over epsilon depth or something like that.
Right.
Like so it's like they suck.
Yeah.
And you can just look at the architecture, right? And be like, even if you're just trying to train an MLP to just fit X squared, right? Just look at the architecture and try to come up with try to see if you can come up with a set of weights that give you X squared. You can't, right? You can approximate it on finite data and finite domains, but you can't actually learn X squared with an MLP.
Yeah, I see. I guess I just saw what somebody did on images, and they showed me something. It was just like a very, I don't know, it's pretty simple. And it's like, oh yeah, we got to sample more translations here because it sucks on, training translation invariants. Oh, we got to add more rotations at this point. And you just, he showed me what the augmentations were along the training limit. And, like I was like, okay, I can kind of believe this, and it works.
Makes sense.
Well enough to to do well on image classification.
Sure.
I don't know.
No,
To me, this is like not as part of a task.
No, I think it's different. I think it's harder. Image classification is you need to get basically in the right neighborhood in the state space, and then you have a discrete decision boundary. Here, if you're near the origin and you're just a little bit non-zero, then you get moved a little bit, and you're a little bit more non-zero, then you move a bit more, and then you get kicked out, right? That's what's happening.
Yeah.
Finding error.
Yeah, and discrete classification has always been easier than like continuous regression. So
This is continuous regression in a dynamical system. So
Right.
every mistake you make compounds.
I see.
that's why classification was like the first things to work, because it was like
But
it was much
does it
easier.
bother you guys as much as it bothers me? Zero input leads to what you're seeing right there. That's
Well,
crazy.
I mean, you would need to have like a super dense sampling. Take this interpretation of MLP suck at multiplication, right? And then you can only approximate it. You have to have a super dense sampling of all of the other states with the zeros and zero to guarantee that you get
They're correct. Or the result that feels intuitively right.
Yeah. Now, if you had originally parameterized your dynamics as something control affine, that's a different story. And that's what I learned very quickly.
All right.
Well, no, because control affine by construction is.
No, I know.
Zero,
Yeah,
right?
yeah.
So,
Yeah, I agree. That was a very controlling answer. Yeah.
Like that
That's a good answer. I just
You say that like it's a bad thing.
no, it's not a bad thing.
continuous like regression sucks so much that for imitation learning for a year, the best method was actually predicting action buckets discretely, and then maybe adding a little bit of offset, which could be good or which could be bad. So like discrete classification is just much easier. Also, no, that
I have another question. So I'm trying to understand the difference between the augmented Lagrangian and your method.
we have this different architecture, which is we take the neural network, we pass it through a sigmoid, we add this lower bound and multiply it with the upper bound minus lower bound. That just makes sure things work out by construction.
Okay. And this notion of memory which you have, it's different, right? They don't have
No, the notion of memory is what provides this lower bound and this
this
upper.
lower bound, upper bound. Okay. Right, and the loss of the constraints is only on those points around the memory, I guess.
It's all the points in the data set. The loss is on all the points in the data set. Some of the points in the data sets are memories, and at those points, the loss would be 0.
No, can I go to the next slide? So the loss on the
Right.
constraint loss, right? C of S and C of S prime.
Right. So so this is also a gamma over here. So it's the constraint loss is also between the constraints given in the model M and our constrained neural network, gamma of f of theta. Sorry again, I need to make my terminology much better in the slides and in the paper. Yeah. Was that the confusion, or is it something else?
Got it. Now I got it.
Cool. Okay.
That's great. Thank you so much.
Thank you. Everything good?
Yeah, everything is good. Thanks for the talk.